Now, the important point here to make sure is that if an Eve was watching throughout this process, she won't know what K is. So let's see what Eve gets to see. So Eve sees A and B. Well, A is G to the A modulo P, and G to the B modulo P. Why can't Eve compute K? Exactly, because you cannot get little b or little a, because this is it's a one-way function, it's hard to invert. Okay, the discrete logarithm problem about which we just learned. Here, this is a discrete logarithm problem. It's hard to invert. So because of that, Eve cannot compute A and cannot compute B. And you need A and B to compute G to the AB. Yeah, question? Yes, they both need to know G ahead of time. So these are public values, public shared values. So it's true that they're shared, but they're public. Okay, everyone can know them. In fact, Alice could even send to Bob, hey, this is the G and the P I want to use, and it's okay if Eve sees that. Okay? It's hard to exchange a secret that's shared. And this is what this protocol tries to do, is to exchange a secret that's shared. Okay, so it's really, really interesting that they managed to agree on the same secret without Eve in the middle being able to see that secret. If you multiply these two values, you're going to get G to the A plus B. But that's not G to the A times B. To get G to the A times B, you need A and B at least. Okay? So Eve cannot compute G to the AB. So this is basically what you do. Whenever you visit a site like bankofamerica.com, the first thing you do is your browser does a key exchange protocol, Diffie-Hellman key exchange protocol with Bank of America, and your browser and Bank of America's web server, they agree on a key, and then you have your secure communication encrypted using symmetric key with the key that you agreed upon. Okay? So basically, this really relies on the assumption that, you cannot break the, discrete logarithm problem, so that that the LP is one-way function. And actually, there's a bit more of a stronger assumption that it needs. This is definitely necessary, but it actually needs something a bit stronger, namely that you cannot compute. So an attacker cannot compute G to the AB modulo P from G to the A, G to the B modulo P, and also G. Okay. But you can see why the discrete logarithm problem must really hold here, because if it doesn't hold, then the attacker will compute A and B, and then they can compute G to the AB. Any question? All right, so that's great. This is all secure as long as Eve is just eavesdropping. If Eve were to be more active, more malicious, if she were to actively start changing messages and modifying messages, then this protocol by itself would not be secure and would have to do something to secure it. So can you guys see what happens if Eve is actively messing up? What could happen if Eve is actively messing up these messages? Exactly. She can send her own public key to Bob, pretend she's Alice to Bob, and pretend she's Bob to Alice. So let's see how that would work. So this type of attack has a famous name. It's called man-in-the-middle attack. Okay, so the man-in-the-middle attack is, classical type of attack in cryptography. So you have Alice and Bob, and they want to talk to each other, but they don't realize that, let's call her Malice, is in the middle, okay? They don't know that Malice is in the middle. So Alice is going to send her G to the A modulo P. Now guess what? Malice is also going to have her own small secret M and her own public key. Okay, so she's going to send to Bob G to the M modulo P. Instead of Alice's public key, Malice is going to send her own public key. And then Malice is going to reply to Alice with her own public key. So Alice is going to think, oh, great, this is coming from Bob, right? And Bob is going to reply to Malice with his public key. And because Bob is going to think, okay, I'm going to send this to Alice. So note what's happening. Alice gets this value, thinking it's from Bob, and raises it to the power of her secret A, and she's going to compute a K that is G to the AM modulo P. Okay, so basically she did an agreement between Alice and Malice. She agreed on a key with Malice, not with Bob. She thinks she agreed on a key with Bob, but in fact she agreed on a key with Malice. Well, guess same thing. Malice can take G to the A modulo P and raise it to her M, so she obtains G to the AM mod P. Okay, so she obtains the same secret that Alice obtains because essentially Malice and Alice agreed with each other. Now Bob similarly takes what he gets from Malice, thinking it's from Alice, and raises it to the power of his B, and he gets G to the MB modulo P. So this is KMB. And he thinks, hey, this is my key that I agreed with Alice, but in fact he agreed with Malice. And similarly, Malice takes what she gets from Bob and raises it to the power of her M, and she gets MB modulo P. Okay? So now Bob and Malice agreed on a key, and Alice and Malice agreed on a key. And Alice and Bob have no clue this happened. So right now, Alice is going to start sending her encrypted communications, encrypted with the key between Alice and Malice, okay, all her secret messages. Malice is going to be able to decrypt them, read them, and send whatever Malice wants to Bob, encrypted under the key Malice agreed with Bob. And Alice and Bob might never realize that there's a man in the middle.